Hello, everyone. I'll now present my joint work with Dorit Aharonov, where we prove two combinatorial MA complete problems. We know that there are a number of settings where randomness helps a lot. So for instance, we cannot imagine cryptography if you're not able to pick a randomly fresh secret key. But on the other hand, we know other settings where we expect randomness not to help. So for example, we know that if pseudo-random number generators exist, and this is implied by several widely believed circular bounds, then every problem that can be solved with randomized algorithms in polynomial time can also be solved by deterministic ones. So we are in an embarrassing point where this type of statements P equals BPP should be true, but it has been open for decades. And the focus of our result is trying to understand this need or not, this need of randomness in the non-deterministic setting. So more specifically, we're interested in an MA versus NP problem. So almost all of you should know what NP is, but let me just recall it. We say that a language is in NP if you have a deterministic polynomial time deterministic algorithm D that receives two inputs, X. It is an instance that you want to decide if it's a positive or negative instance of this problem, and a proof Y. And we want this algorithm that, this algorithm has the following properties. We know that for all positive instances, there must exist a proof that makes this deterministic algorithm to accept. But for no instances, no matter which proof is given to this deterministic polynomial time algorithm, it should reject. Since NP is a cornerstone of classical complexity theory, it has been extended to different settings. So for instance, in the randomized setting, where we have MA, that stands for Merlin Arthur. The definition of MA is it follows closely NP. So now we still have an input and a proof, but now we have a polynomial time randomized algorithm that should accept or reject X. And in the definition of MA, we can say that if there exists, for yes instances, there exists a Y that makes this randomized algorithm to always accept, and you can assume it without laws of generality. And for no instances, we want that for every proof that is given to this randomized algorithm, this algorithm should reject with high probability. As in P versus BPP, we also believe that these two problems are the same, and this is the non-deterministic and the de-randomization conjecture. And these are implied by the existence of pseudo-random generators, believed circular bounds. But again, the problem if MA equals NP is still an open-wide problem. One way of trying to solve this conjecture is trying to pick an MA complete problem and showing that this MA complete problem is NP. But one problem with this approach is that the problem the MA was defined in the 80s, but since 2008, no MA complete problem was known. And Bravo and Terhall, they showed the first MA complete problem coming from quantum computing. Later, other MA complete problems were also developed, but again, in these in the context of quantum computation, or at least with a quantum notation. So this makes us wonder is this a fundamental problem that this a fundamental point that all MA complete problems come from quantum computing? Or can we find new combinatorial MA complete problems that have nothing to do with quantum? And this is the main question that we tackle in our paper. So in our work, what we do is first we propose two new problems. And the first problem is an extension of CSPs to what we call set constraint satisfaction problems. So the idea is that now we have constraints not on a string, but on a set of strings, and on a set of strings, yeah. And we want to know if there exists a set assignment for these constraints that that satisfies all of them, or for all set assignments, there is an epsilon fraction of them that is not satisfied. The second problem that we propose is nothing related to that. Like it has a very different definition, and it asks about finding clean connected components on graph. So let me be a bit more explicit. The input to this problem is an implicit description of a graph. So we have a circuit that tells all the neighbors of a given node. And we're also given an implicit description of a function that marks all of these vertices. And we want to decide if there, between the cases, if there exists a connected component where all the vertices in this connected components are marked, or we want to approximate this property, meaning that for any set S, either there is an epsilon fraction of these vertices that are marked, or the set is epsilon far from being a connected component, meaning that there exist a lot of edges that leave the set S. And with these two problems in hand, we have the following results. So first, we show that the SetSCP problems is actually MA hard for an inverse polynomial parameter epsilon. Secondly, we show that we can reduce SetSCP to this approximately clean, approximate connected component problem. And finally, we show that for every polynomial P, this approximate clean, approximate connected component is in MA. So these three results together say that we can show that these ACAC and SetCSP problems are MA complete. So we finally show two new MA complete problems that are that have nothing to do with quantum, and they are defined and proved on with only combinatorial tools. So now I'll give you a bit more details of how to achieve these three steps. And I will start by the third one. So let me give more details on this ACAC problem. So as I said, the graph is given implicitly. So we assume that the set of vertices are all n-bit strings. And the set of edges are described by a polynomial sized circuit C that, given a vertex, it outputs at most polynomially many neighbors of V. Furthermore, we have also another polynomial size circuit M that also gets as an input one of the vertices, but now outputs just a bit that tells if this vertex is marked or not. And as I mentioned before, we want to distinguish yes and no instances, where in yes instances there exists a connected component that is unmarked, so all vertices in this connected component are unmarked, from the case where all sets of vertices are have either a lot of marked elements or they expand well. So there are a lot of connections between the set of vertices and everything that's outside of it. So as I said, we show that ACAC is in MA, and our MA verification is the following. So the prover just gives initial strings x0, and using the implicit description of this graph, the verifier just performs a random walk on it. And if at any point the verifier this random walk passes by a marked element, then the verifier decides to reject. So we can easily show completeness because if there exists a clean connected component, so a connected component with where all the vertices are marked, then the prover can send any vertex of this connected component, and the random walk does not leave it. So the random walk never reaches a marked element, and therefore the random walk the verifier never rejects. For soundness, we have that from these properties of no instances that every set of unmarked strings, it has a lot of expansion. So so the probability of leaving the set is very large. So with this property, we can show that for any random walk start in any vertex, we reach a marked string with a very high probability. And therefore, we can improve the soundness of the ZMA verification. And this ends the proof or the sketch of proof that ACAC is in MA. We now switch gears to the second problem that we propose in our work, which is called SetSCP. As I previously mentioned, this problem is an extension of standard CSPs to the notion of set constraint satisfaction problems. And because of that, let us recall standard CSPs. And here we have that an assignment is a n-bit string. And we want to choose this assignment that satisfies all the clauses. And the clauses here, they can be seen just as allowed substrings. So for instance, a clause CI could tell that bits I and k, it could have the value 0, 0, 0, 1, and 1, 1, but it could not have the substring 1, 0, for instance. And you want, as I said, they want to choose an assignment that satisfies all the clauses that such that all the substrings are allowed. On the set CSP setting, we now have assignments that are sets of strings. So we have a subset of all the possible n-bit strings. And now the constraints, they're not only allowed strings, but they are allowed sets. So let me be a bit more concrete. So by an example, so if you have a set constraint CI, we now have two sets, and these sets must be disjoint. And here we see that we have a set 0, 0, and 1, 1, and the second set 0, 1. And now a set of strings being satisfied by a constraint is a bit more complicated. And I'll try to explain it by an example. So we say that a set, for instance, that if you have the constraint C1, that is defined as I said before, the first set 0, 0, 1, 1, and the second allowed set is 0, 1. And let us see what happens if you have the assignment, let's say S1, that is 1, 1, 0, and 0, 1, 1. And the first requirement is that the substring of each string in the set appears in some set of C1. And here everything is fine because we have 1, 1 in the first set and 0, 1 in the second set. But on the other hand, if you consider the set S2, we have two strings, 1, 1, 0 and 1, 0, 1. 1, 1, 0 is fine because 1, 1 is here, like on bits 1, 1, and 2. But 1, 0, 1 is not good, so it's not satisfying the set constraint because the substring 1, 0 doesn't appear in any allowed subset. The set constraint, it tells, okay, the first one is set constraint is telling what are the allowed strings in the set, but now we have a stronger notion that tells strings that should come together. So for example, I'll keep the same constraint, but now let's say if you have the set S1, if you have the string 1, 1, 0, since 1, 1 comes always with 0, 0, so if they appear in the same allowed set, what we also require is that if we replace 1, 1 by 0, 0, the remaining string, that 0, 0, 0, because we keep the third bit or all the remaining bits, it should also be in the set S1. And for example, if you have just a singleton, then it does not change anything, right? If you have 0, 1, the string does not have any neighbor in this allowed set, so on its own, it is okay in this set. And just to say how would be an example where it does not happen. So for instance, if you have S2 that does not contain this string 0, 0, 0, then this set S2 is not good, because if you have the string 1, 1, 0, this string is missing the string 0, 0, 0, because 0, 0 and 1, 1 appear in the same allowed set. So here I just wanted to give a glimpse of how what it means by set constraint to satisfy, like a set to satisfy a set constraint or not. And just to be a bit more concrete, as I said, SetCSPs is an extension of CSPs, and this is the case because you can convert CSPs to SetCSPs where all the sets are singleton. So all the allowed sets just contain one element. And in this case, this second restriction, it does not appear anymore, and then you have standard CSPs. But the power that comes from SetCSPs is indeed having more than one more than a singleton here, and this will allow us to prove MA hardness, as I'll tell shortly. So as I said, what we show is that SetCSP is MA hard, but before going to that, we have to define some notation. So we tell that a set S has the unset value according to some clause CI. And this value is just the number of strings that violate the properties for this constraint CI. So either strings that are now not in an allowed subset, or strings that are missing a second string that are not in this set S. And in order to keep it normalized, we also we divide this number of strings violating CI by the number of strings in the set. And we just generalized it for the unset value for this set according to the all set constraints. And this is just the average of the unset value for every CI. So a bit more concrete in our result now, we show that there exists some polynomial P such that if you're given as input set constraints, then we show that it is MA hard to decide if there exists some set S that has unset value equals 0, so a set S that satisfies all the constraints, or for every set of strings, the unset value of this set of string, there's unset value according to this all of these constraints should be above some inverse polynomial. So it's very far. It's somewhat far from being satisfied. And now I'll try to give a glimpse of how we prove MA hardness of this problem. And but in order to do that, let me give a step back and go back to the NP completeness and Cook-Levin theorem and see it in a different way. So in the Cook-Levin theorem, we first start from a Boolean circuit. So it has some input, you have some gates, and you have output bit. And the question is there assignment to the input variables such that when you propagate these inputs, you have the output 1? And the way the Cook-Levin theorem goes, in like a different way of seeing it, is that you want to consider the history string of the circuit. So you want to assign like these variables to all of these to all of the wires and see them as a string. Right, so we put all of them together, and you want that to add constraints. So you want in the CSP you add constraints that indeed check if the correct positions are form a correct history of this circuit. So let's, for instance, the bit corresponding to 1 should be the end of Y1 and Y2. And these constraints, so as I said, they should check two things. So first, that these variables have the consistent values, and secondly, the output bit is 1. So the first, at first, would be attempted to say, okay, what happens if you, so this works for NP, but for this to work for MA, we should replace these variables by a random value, right? So the idea is that we should replace them by some values R1 up to R, let's say, K, and would be attempted to say that, oh, then you could try to use the same the same reduction to have a history string. But here the crucial point is that how can we ensure that these random input bits are indeed random, and why aren't they adversarially chosen? And in order to enforce that you indeed have random bits, that's how we use set constraints. But so let me extend this notion of history string to the notion of history set. And to show MA hardness, we need a bit more of structure. So instead of having just a Boolean circuit, we want now it to be reversible. But that's no worry, because we can do it without loss of generality if you add some auxiliary input 0, and we choose a gate set that is reversible. And luckily there is. So if you have NOT and the CC NOT gates, they are a universal gate set for classical computation that is reversible. And now, instead of having a history strings, what our idea is to put every snapshot of the computation in what we call a history set. So we want to collect all the snapshots of the computation for all possible random values. But in order to do that, we want that the snapshot of step 0 not to be mixed with the snapshot of S1. So because of that, we will append a prefix that tells what's the timestamp of that snapshot. So for instance, if you have a time 0, we have 11000 as the input. Then at time step 1, and for technical reasons, we put the clock, like this timestamp, the clock register as in unity. So if you have this input at time 0, then you should have 100 as a snapshot of time 2. And with this, so you have this random value 00 here, and then we can add all the steps of the computation to this history set. And the point is that we do this for not only for the value 00 for the random coins, but then we add for every possible value. So we add all the snapshots when the random coins are, for instance, 01 and 10 and 11 and so on. And what we're able to show is that you can add set constraints that verify if the history set is at least close to be correct, meaning that the set contains strings that first the clock register is correct, then that at timestamp 0 you want that all the auxiliary bits they start with like they are initialized to 0, for instance. Third, and one of the most important parts, we want to show that the history set contains the history of computations for all random coins. And finally, as in the NP case, we then check if this history set contains all the computations, so all the snapshots are there, and that the output snapshot contains the output bit 1. So these are the set constraints, and I won't dive into the details what they really mean, but I just like to point out that this set constraint that check if all random values there are there, and they say that at time 0, if you have a random bit 0, you should also have the random bit 1, and vice versa. So this is the key point that allows us to enforce that all random coins should be in the history set. And this finishes the proof, or at least the glimpse of the proof that SetSCP is MA hard. Now, the only remaining part is showing a reduction from SetSCP to ACAC. And here, so we assume that to have an SetSCP instance that consists of m set constraints. And then we consider the implicit graph where the vertices, as I said, are the n-bit strings. And we consider two strings to be adjacent if there exists some I, such that these strings are neighbors via CI. So this means that these two strings are neighbors if they should appear together in the set assignment for this SetSCP. And notice that this can be computed in polynomial time, so we can give an implicit description of this graph. But for the input of ACAC, we also need this implicit description of the function that marks some vertices, and we say that this bit string is marked if and only if Z is not in one of the allowed sets of CI. So Z is a string that should not be in the assignment for the SetSCP. So given this reduction, what we're able to show is that if there exists some set S such that it satisfies all set constraints, then S is a connected component in G, and moreover, S contains only unmarked strings. So it means that if this set constraint, the set CSP instance is satisfiable, then the graph has a connected component that is unmarked. Second, we show that if for every S, then the unset value of S according to this set CSP instance is at least epsilon. Then for every string, first every set S, it contains at least epsilon over 2 fraction of marked strings, or the expansion for the set, so the number of neighbors is at least epsilon over 2. And this shows that if you have a null instance of the set CSP, then you also have a null instance of the ACAC problem. And therefore, since we know that set CSP is MA hard and ACAC is in MA, then what we show is that ACAC and set CSP are MA complete for when the gap, or the promise gap for both problems is inverse polynomial. So let me just conclude with some further work and open questions. So by using the same arguments that Dorit, Aharonov, and I had in our 2019 paper, what we can show that if instead of considering inverse polygap set CSP, if you consider constant gap set CSPs, then this problem is actually an NP. So in other words, what it can show is that if you have some sort of set PSP theorem, so a gap amplification for set CSPs, then you can actually show that MA equals NP. And the backward direction is direct because we have a PCP theorem for NP. So this shows that if you want to show that MA equals NP, there is actually a very concrete way of doing that by showing gap amplification for set CSPs. However, we cannot show that gapped ACACs in NP, and this is an interesting open problem. And our goal is that with our 2 combinatorial NP complete problems, we can now show that many more problems are actually MA complete, and hopefully use them to show that MA equals NP. So thank you for your attention.